Hey, the lecture has gone. All right, so hello. Today I've prepared for you like updated, interesting lecture about convolutional neural networks and not only. So today maybe you know this convolutional neural networks like push it into the history and not to make it a lecture just of historical interest. I like wanted to have some takeaways for you from this lecture, and what we can take away is maybe the design principles, how and why they worked, and maybe some of the properties that convolutions have regarding the equivariance with respect to the shifts, and to kind of better understand these properties, and also to see how they can be carried on to some other architectures like the neural networks on the sets and the graphs. So we will talk towards the end of the course about graph neural networks. And here I will be talking about deep set architectures and deep set neural networks in the context of these equivariances. And so it will nicely connect to the graph neural networks later on. All right, yeah, okay. Let's put a full screen. So we start from this sort of still inspiration and history. And the inspiration came from biological studies, so how the brain works, how the visual cortex works. So these first and very famous experiments, maybe not the first, but the sort of seminal experiments in this direction were by Hubel and Wiesel, who discovered that like they were probing some neurons in the cat visual cortex. And if you show to the cat just some um, flat color, no neuron is triggering. And then if you show some pattern, so some neurons are triggering. And they figured out that the most they are firing these neurons, so neurons are making some spikes, right, of signals. And the most they are firing when you show them like specific patterns that look like these bars. So very contrastive oriented bars, or a very contrastive like a white spot surrounded by black, or the other way around. So the black spot surrounded by white. So these were the patterns that they identified empirically that the neurons respond the strongest. And now if it is an oriented bar like this, then it turns out that, okay, so there are some neurons that are the most responding to this bar, and there are some neurons that are the most responding to such a bar. And then you could sort of identify. So there is this neuron kind of detecting that pattern, and the neuron detecting this pattern. And you can also like remember these neurons and then see, okay, so if you actually move this bar, then the neuron for that pattern would also react, but just a little bit. So it's shown in these figures. So this is some spikes in the or uh, oops. Yeah, let me fix this setup. How do you do? I gotta switch on the mouse in that. I don't know how. Okay, so here is this graphs they are showing, so that the strongest react in some neuron that is responsible for that orientations, but also like the nearby orientation neurons reacting a little bit. So this was one thing, and the other thing they discovered is that, okay, so then these neurons, they are sort of retinotopic. So in the field of view, this pattern is here or there, then different neurons will react on this visual cortex. But some neurons are kind of less sensitive to the position, so they would react whenever this bar appears in some neighborhood of the receptive field, right? So some neurons are like specific to the position, so it would react if the bar is here, but not if it is here. So then some other neuron reacts to this one. But some cells are like reacting to any placement of this bar, and these were called complex cells. So the simple things are detecting orientation maybe and at particular location, and the complex one are reacting somewhat invariant to the position. So this was one thing, and then yes, and then there was, I think, since long time, this idea of hierarchy of representations, so that okay, so there is these first layers that are detecting these basic edges in the human brain, and then somehow they produce their own responses, and then yeah. Well, we have a separate neuron for each of the orientations, right? So if the picture gets rotated, then a different neuron will be reacting, right? Not the same one, but a different one. And since there are all neurons in all orientations, so some of them will be probably reacting, maybe and I don't know. I think if you tilt your head like this and try driving your car, you will notice that it's not exactly the same. So you don't have this like complete invariance or equivalence to the orientation, and it's taken care of by duplicating the mechanisms. Yeah, yeah, yeah.
So there you have like all the orientations, you get it, but if you go higher, maybe you lose this orientation invariant because you don't need it in practice to gain the rotation invariance. Like on higher levels, there maybe the outputs of the neurons would stay the same independent of rotation. No, but I mean, if you see face upside down, it's difficult for you to recognize it, difficult for you to see the mistakes, and so you don't really recognize things as well when they are rotated, like driving a car like this.
Yeah, it seems to stay to quite depth levels. So this. Let me continue. So the idea that okay, so once you have some cells which are doing some simple job, then there could be some other neurons which are taking inputs from these simple cells and kind of doing something with that, and then somehow producing a combined input, and maybe they would be like okay, progressively detecting some combinations of the edges, so some like basic patterns, and then reacting to the more complex configurations, and then up to recognizing the whole object. So this is like the idea, which is natural from the two sides. First, you could describe objects by parts, so you kind of want to detect parts, and then you're able to say, so the face is okay when you have an eye and the nose and something else. And the other side of that is that okay, so you do have only this basic little neurons, so they must kind of combine and aggregate the information somehow in order to do the complex tasks. So basically to solve a complex task, you kind of need the functionality to solve the simpler tasks. So this is the neuroscience inspiration, and in the 1980, there was already models of that to run in the computer. So we discussed about perceptron. So for the perceptron, at the time that was maybe 1970s, right? So they had computers were quite limited. So they had one model was emulated in IBM. The other was in this hardware that we discussed. Now this was meant to be a computer program, but designed with all this biological inspiration. So what you see here in this figure is that these two kinds of cells. So these simple cells that are supposed to react to some specific patterns, and then they are at a specific position. And the complex cells, which are, so they were engineered to do an average or some normalized average response in a receptive field. So they were, now because you might have like these different orientations, you have to have multiple detectors at each position to detect this, and that, and therefore there are these multiple planes. So for kind of each elementary pattern, it will be spatially organized map where that pattern occurs, right? So they had this in the design, and they had this like pooling over the region. If something fires here or here, it doesn't matter. So by this averaging, and this allows you to be more flexible with respect to the input deformations. So if these little patterns are detected in these positions, maybe that's indicative of the letter A. And if they are detected also in some offset positions, so exactly the same patterns or like very similar patterns, it looks like this deformed letter A. So it was actually, I don't know if it was a collective or just this one researcher who, this guy I know, he worked for this continuously for, so this is some neocognitron. 10 years before he was working on cognitron, 10 years after he was working on some neocognitron with feedback loops, or I don't know what else. But you recognize that, so if you have seen like convolutional neural networks, you might already recognize, okay, so here we actually have connected to both ends, to the visual, so the neuroscience inspiration scene, and actually you recognize a lot of the current neural networks, convolutional neural networks designs in this, especially the simple cells and these complex cells which are doing the pooling. And it was trained unsupervised. Also quite interesting. So how? Basically, like unsupervised clustering works. So if there is a cell that happened to react the strongest to some pattern, then its weights are emphasized. So you could like recall, maybe think of this unsupervised clustering procedure where you have some points and you put randomly somewhere some cluster centers, and then you say, so this point is close here, this point is close here, this point is close here, and you move this cluster center to be yet closer to all of these points, or to their average. So there, if some cell was responding the strongest out of the neighborhood to a specific pattern, then its weights were kind of reinforced to still stronger react to that kind of patterns. And then by that way, like it was just presented different images, and the cells learned via this clustering kind of learning to sort of, then you don't provide the supervision like to ask this network to recognize the letter A from letter C, but you observe that in the process all letters A, they form in the same cluster, so the same kind of cell reacts on the output to them as compared to the letter C. Okay, so that was like a neuroscience inspired approach, but there was also a comparative approaches which do not necessarily like was thinking about, okay, let us have I will be Yeah. No, so this were less concerned with feedback loops and the biological inspiration, but rather as, okay, so how can we kind of do the object recognition? So we want to find some visual keywords and do sort of indexing to retrieve the images from our database, which where these visual keywords are present, and they build a hierarchy of these visual keywords by kind of joining. So the first level was this type of detectors, and maybe that there is inspired by vision and biology, but then, okay, combining them into creating some combinations. But already, like, creating these combinations, so the learning here was, okay, which combination gives us sort of is more discriminative with respect to retrieving the images. And then they were creating combinations of combinations, and this is like levels of these features at different levels of hierarchy, and then they could also like project back to what are the active things which were found in the image, which were useful for the indexing, and it was recognizing. So that was engineered to give you fast retrieval, so fast recognition.
And this uses learned features or crafted?
Learned, but learned statistically, so like layer by layer, and in each layer you compute the statistics and find the combination which has some good properties, like that it is discriminative and
Kind of like decision trees, kind of like finding the combination itself.
yeah, I must say I don't know like precisely for this machine, but yeah, there was. So this is not a neural network, no backpropagation, but yet it also was doing this hierarchy of parts, and then it was like selecting based on the statistics, the feature combinations.
More like picture model, something like that at the time, yeah, something like that.
Okay, and now like we go more towards the engineering. So the famous network by Jan LeCun. So he worked gradually on these things. So first they hand designed all the weights and had a small neural network with, I don't know, 3 layers or so. And they implemented it. So it was some neural network to recognize paychecks in ATM machines. I don't know why they had to have paychecks in the ATM machines, but yeah, so that was it. And then they were improving. So then they did the backpropagation training. So, okay, computing the gradient and training the weights. And then, like, okay, also increasing the number of weights. So here you also see this reduction of the resolution steps. So first you detect something, and then there is some aggregation happening that um, decreases the spatial resolution, and maybe I think they were doing max pooling, if I'm not mistaken. So then in each maybe 4 by 4 pixel, we take the maximum response. So that corresponds right to sort of reacting regardless of where precisely this feature was detected. And then there was at some point, okay, before the year maybe 2011, there was rather sort of cleverly engineered visual recognition systems and trained with pieces trained with classical machine learning. But then at some point somebody, okay, took a big enough neural network and trained on all of the data, and that surpassed by a lot. So that increased by a lot the performance in this visual classification, image classification. Okay, and yeah, so I will tell you a bit later about what is in this picture, but it's kind of that architecture. So you have the some convolutional features detected, so some kind of patterns detected at all positions, and then some pooling layers, and then combining that. And then since then on, okay, so people try to, okay, let's make a better architecture, let's do this, let's improve the training, and so on. And then it's, you see, that's already quite outdated, this plot. All right, so the part two, we discuss what is actually, so now we talked about in inspiration and history, and now we like look what is really the convolution, and um, a little bit of what its properties. So mathematically, you could like write the equation, but it's just the best is just the picture, right? So the convolution is we have some weight kernel, so let's say template, and we put that template at every position at our input, and then we compute like a dot product of this template with the part of the input at that position, and this is going to be our response at this point. So it's just this linear operation of like having this weight filter and sliding it over the image, over this 1D sequence or over the image if it's then this 2D template over the image. Technically there are two kinds, so you could say in math often the convolution is defined and the cross correlation is defined slightly differently. So in the convolution you kind of have to flip one of the inputs. So for example, you flip the weight template with so this, like according to the definition, that it must either the input signals are read in the flipped order or the convolution weights are flipped in the reverse order, so you could equivalently transform between these two forms. And in the correlation it is sort of without the flipping. It's the correlation is easier to think of for us maybe in this context. And once we are going to learn the weights, it doesn't matter actually whether you are flipping this mask or not. So in the deep learning, they are actually more or less identified together. So you don't distinguish. So you could call it a convolution, whereas the formula will be computing a cross correlation. Right. Now here are some examples with these 2D convolutions. So you take an image and as a filter you put maybe such a kernel. So this is our weight mask. And then if you slide with this filter through all positions and compute the result, you get a blurry image, right?
So the resolution of kernel is smaller than the image in this case, right? It's just like it looks like the same as the image, but maybe you made it to be smaller.
It
Right?
You see the pixels?
Yeah, I see. That's why I'm saying so. I'm just like, it looks like the same size in the slides all this time.
Okay, yeah.
Just making sure that this is not the real size of the kernel, like in the pixel.
Okay.
There's this classical picture when the kernel is like smaller and it's like
Yeah, yes, correct remark. I enlarged it for visualization, but maybe now it's not clear that what is happening. Yes, it is like a small kernel that can be sliding over the input. And now, suppose the kernel is this, then what it does, it is sort of averaging over all such relevant positions, and this makes a motion blur, right? Now maybe like little exercise for you. What will happen if there is this only one pixel active in this kernel? What will be the result? Yeah, back there. Yes, correct. So this will just shift the image, And this one in the bottom. Yes, please.
Edge detection, but only in that specific direction, like edges that are.
Yeah, exactly. So this. Yeah, so this will react the strongest when in the image they will be of different signs, something of this shape, right? So something like edges. And here you see, like depending on the sign, it's either black or white, right? So it is a kind of signed oriented edge. Now we intuitively see what happens with these convolutions, and let's talk about now invariances and equivariances and the difference between two. So if I have an image and I shift this image, okay, here I made a nice picture that the sky stayed at that position where it was, which would be because it's far away. So it's not technically exactly the shift of the whole image. But suppose you are like shifting the image. You still want to classify this. So if you are seeing that this is a flying balloon, then after you shifting this image maybe by a little bit, you still want to preserve your classification, so to say that it is still the same flying balloon that I see, regardless where in my field of view it occurs. So that's invariance, right? But then if you are doing like segmentation, so you want to say, okay, for each pixel you want to label whether it is a balloon or sky, then if the image shifts, you want that your segmentation would be where the balloon is, right? So you want to shift it exactly to the same position where the balloon has shifted. And that's called equivariance. So this scene, the first scene was called invariance. So we classify regardless of the position. And if we have on the output like one response per pixel, then we want equivariance. So we want the output respect the shift. So it actually, what we want is that it should not matter whether we take this image and segment and then shift the segmentation, or we shift the image and segment and then obtain the result. So we want this to be equivalent, and that's equivalence. And clearly, like going over the image with some template and doing something locally at that position, while not knowing the global position, but only the relative information, like local image in that context, maybe local coordinate offsets, is having this property of the equivariance, right? But we can even break it formally. It's not very hard to break it down to see how things work. Okay, so these are our pixels, so they are organized in two-dimensional grid. And for the purpose of analysis, let's just think of one-dimensional chain of pixels. So kind of we'll talk about convolution in one dimension. And then here on the top, I show you like a linear transform which performs a shift of the input. So if like we have the diagonal offset and it offsets cyclically, so that this one appears on top here. So if you apply such an operator to any input, so that the input cyclically shifts. So that's our shift operator. And we want to be invariant to the shift. So mathematically, we can define this shift as that pixel which was at the position I will move to the position I plus 1, right? So this is going to be indicator like this. Okay, this is written without this cyclic thing. What we want to do. So this is our shift operator, and we want to ask the question like, okay, what is the linear operator on the sequence which is equivalent to the shift. So can we describe all the linear operators that are shift equivalent? And this is the condition of the shift equivalence. So it says, okay, so our linear operator must commute with this shift, so that it doesn't matter whether we first shift the image and then apply our linear operator, or first apply our linear operator and then do the shift of the result. And this must hold for all possible inputs. And therefore, you gotta have this equality that just as linear operators, they must commute. So the shift must commute with the linear operator that we are looking for. And if you substitute, so if you substitute the definition of the shift, it turns out then, oh, okay, so this linear operator gotta satisfy this simple equation that the next row of this matrix must be like the preceding row of this matrix, but shifted by 1. And this is a property of matrix. So matrices with such property are called circulant matrices. So they look like this. So suppose on the row it is this sequence of weights, and then it gotta be repeated like this along the diagonal. And that's exactly what the convolution is doing. So the convolution, so if you apply this matrix to the input, it is like, okay, to each position you apply the same filter, but at a different place. So yeah, so we have this conclusion. It says, okay, if you want a linear operator which is equivalent with respect to the shift operator, it has to be a convolution or cross correlation, depending on how you interpret this weight matrix. So we are arriving at the convolution from the sort of basic principles, right? So why to do convolutions? Now, okay, now you see, okay, I want the property that my segmentation would be equivalent with respect to the shift, and then I ask, okay, what's the linear transform? So the basic thing what we can do on the input is some linear transform. What is the linear transform which would have this property? And then the answer, it has to be a convolution. Okay, now let's go like a bit deeper into that. So there is more to this. It turns out that if two matrices commute, then they have the same eigenvectors. So if you look at the, just a second. So if two matrices commute, they share the eigenvectors. And it turns out that eigenvectors of the shift matrix are the Fourier basis functions. How does it work? So like 1D, so think of 1D. So the Fourier basis functions are these sort of sine and cosine functions in this complex formulation. So if you shift this sine function, then it is still like can be composed out of the sine and cosine with the same frequency, right? So that's what happens in the complex numbers. So you have this one and the other one, the cosine, and then I guess the eigenvectors are also complex. So if you shift that, you kind of receiving the same eigenvector, so the same pair of sine and cosine, but with the different complex multiplier, which changes the phase, right? So that's how roughly that is going to be. And then it turns out that from this we could conclude that all convolutions you could write, you could decompose them in such a form that it's going to be in this Fourier basis, it will be some diagonal matrix of which is the Fourier transform of your weight kernel, and then on the left and on the right this basis function. So any linear transform, any convolution can be then represented in this form, and from this we could also like derive the convolution theorem. So, all right, if we just substitute this definition and apply it to some vector x, just by putting the brackets differently, you get the convolution theorem that says, okay, you can take the Fourier transform of the input, Fourier transform of the weights, do the dot product, and do the inverse Fourier transform, instead of you know putting the weight filter at every position and calculating these dot products. So you could do this, and for like big image and a big template, this gonna be faster. But we are interested in this not for that reason actually, but for some other reason. You will see. Are you following for this? All right. Now we are back to our like biological inspiration. So here I show you the Fourier basis. Not all, maybe truncated, right, in the frequencies. Here on the right, you have what is called Gabor filters. It's a mathematical model for these cells in the V1 cortex. So they made a lot of recordings from these V1 cells, and then the question was, okay, so what are actually these cells are really reacting to the most? So how the best to describe how these cells are reacting to? And it turned out that such a model that follows this design principle. So this Fourier basis we got kind of out of the shift equivariances, right, in some sense. And these Gabor filters, they can derive it from shift equivariances and some additional design principles like that. So you want a linear filter which is shift equivariant, and something also with respect to the change of the scale of the image. So some additional principles with respect to that. So this is why they are kind of not so they are attenuated towards the in distance from the center. And this is the image showing these Gabor filters. And now look, this is the image showing the weights learned by a neural network in the first layer. So if you take a big convolutional neural network and train it on some task, does not matter very much on which task, sufficiently general and complex task, then it turns out that the first layer might learn something like this. And I guess you might have a question like, okay, what is going on? Why is it learning that? So I cannot pin it mathematically for you at the moment, precisely, but you see there is some connection, right? Maybe the reason is similar to why the Fourier transform is used for video and image compression, right? Because you have only that many of these filters to learn, and it's like, so yeah, there should be, it seems that there should be also like a mathematical reason for that. Yeah?
Once you present the colors in the CNN blade fridge, like some of them are black and white and some of them are colored.
Yes, thank you. It is, so here we were talking about like grayscale images and the Fourier basis for that. Now, if you have color images, you need to do something more. So your template could be also reacting, could have separate coefficients for the three components of the input. And then it could be visualized also as an image, right? So as a colorful image. Yeah, so this is like something to think about, something intriguing, and likely having like a more detailed mathematical explanation to this. Um,
Anyone tried like fixing the first layer and just putting it as a Fourier basis functions and only learning like the later layers? Does that work? Because it seems like very similar to the Fourier basis functions.
yeah, I think they did, but maybe it's not sort of the mainstream and not commonly done. Yes.
Some way to generalize the Fourier basis for the colors also, like, because it seems to detect the patterns only, but if there's some, I don't know, easy and intuitive way to say just, I don't know, it would be just the same thing for colors or.
Well, the easy way would be to do it, in a separable fashion. So, like, okay, this 2D Fourier transform is, let you first do it for the x direction and second for the y direction, and now you can also imagine do it in the some temporal direction or the color frequency direction, color direction. Well, I don't know whether it is natural or not with respect to this particular three RGB colors that we have. So okay, it's a good question. So I don't know what exactly their model is here. What do they do with the colors to model the human vision? All right. Now we have maybe I would about 15 minutes to CNN engineering, just to explain how then like the networks were designed and what are the components and how that all works together. And for that purpose, it's convenient to take this architecture, which is it has a nice picture which will be convenient for us to understand the functioning. So compare it to this AlexNet that I showed you before, that was maybe a bit more interconnected and complicated. So this is like interesting, and it contains most of the constructive elements and most of the ideas how the things works. So it has, what you notice is that like it has these stages of doing the convolutions. So maybe a couple of the convolutions sequentially, but then there are these reductions. So in the spatial resolution, right? So this was original image maybe, and then you detect maybe 64 filters. Using 64 filters, you detect like some basic features in the image, and this creates you like then sort of the image with 64 channels instead of the 3 RGB channels. And then the next layers have to process that, right? And so you do this, and then you decrease the resolution. So how we'll decrease the resolution? We take an average of the maybe responses every 4 neighboring pixels, or take the maximum response of this 4 pixels. In practice, it doesn't matter so much. And then, okay, once you reduce the resolution, you can afford to have more channels to run the filter bank with more of the filters, and you have, so here you have 64 of the channels, and then after decreasing the resolution, you could afford to have maybe 128 channels, and then if you decrease it even by a factor more. So every time you decrease the image size by half, the number of pixels gets decreased by by a factor of 4, right? So actually, when we are decreasing the resolution on the side by half and doubling the number of channels, the two things are happening that I'll come back to what I was saying. So let's detail the pooling. So we discussed, so to reduce the resolution, you could do these 3 things. So maybe compute the average in this, or compute the maximum out of these 4 locations and do it for every such 4 tuple, or compute the average over these colored locations, or simply subsample. So okay, you say I don't take the average or the max. I don't care about all of these outputs. I assume that all these features will be kind of similar in the nearby pixels. So I just take the first one in this top left corner, for example. So you just ignore these outputs, and then if you are intending to ignore these outputs, you don't even need to compute these outputs, right? Obviously, so you just need basically to compute at these sparse locations. So you gotta go with your filter and now slide it not one by one pixel, right? But you gotta shift it by more pixels, and that's called stride in the convolution. So this can be convolution with stride, can do also this resolution reduction.
Can I ask something about the pooling?
Yeah.
Actually, like as far as I see, it's always use max pooling is preferred instead of mean pooling. Like is always max pooling. Why is it preferred instead of mean?
Yeah, it's like hard to say. So maybe you want to react to the strongest response in the neighborhood. That's maybe some intuition. Maybe it is a nonlinear operation, because if you like put it right after the convolution, then the max pooling would do a little bit more than just convolution and averaging, because that would stay linear, whereas the convolution and max would do some nonlinear job as well. Maybe just empirically in some cases that works well. But I have seen that people were obtaining good results with either of these 3 kinds, and maybe this one is the simplest, so it saves you some computation. So this is also like a popular choice. Maybe okay, so maybe it's true that max pooling is a little bit better, but I'm not sure whether it holds only for the low layers or throughout the whole network. And it's not that like absolutely that it is always better, right?
Maybe I would say like it's more like empirical observation that it usually works. And my intuition behind is like you often combine convolutions, max pooling with some nonlinearities, usually random, which is like then it causes some of them to be 0, and then if you do some averaging and stuff like that, maybe there's some interference with that. I don't know. Maybe it's because of the loss at the end, but because at the end the loss is typically like you have to produce the highest score possible to win. Yeah? So maybe this somehow influences something on the way, but the idea is just like just the invariance, yeah, like shift invariance, and there are ways how to do it. It's maybe like in brain you also have like winner take all. Like usually you take this, and when there is something, you just do it like this maximum. So maybe it's also like
maybe it's make less sensitive to noises too.
Could be, yeah, like in brain for sure. Here, yeah, maybe.
Well, it has this appealing intuitive property that, okay, I want to respond to the presence of this object regardless of its location, right? So it could be doing something like that.
Oh, okay, so yeah, so maybe if there is something different, you don't want to average with it. You just want to say this is there, yeah?
Mm-hmm. Yeah, yes.
Maybe that.
Now, okay, so what I was telling. Yeah, so if you reduce the resolution and double the number of channels, this is what happens with respect to the memory that you need to represent all of your activation maps, and with the respect of the memory that you need to model all your kernel weights. So this is what we discussed. So the number of channels doubles, and the image size gets reduced by half. and the memory that you need to store this result of all the filters applied at this current stage will be like proportional to the squared image size, right? Proportional to the number of channels that you're gonna have on the output, and maybe proportional to the batch size because you want to train in parallel and you want to fit that. And the weight for the memory, because the common convolution, so we discussed like the convolution in the image, but now we also have this convolution from the like sort of input with C channels to the output with also with some other number of channels. So we're gonna have as many filters as there are output channels, and each filter has to look also at all of the input channels, not only at its spatial like 3x3 window, but also at all the information in all of the channels in the preceding layer. And hence it's the memory that you need is proportional to the squared number of channels, so like from the input to the output. And then some like special size of this filter kernel. Now, and the last plot shows the computational cost of applying that filter on that map on that tensor of the activations. Maybe what conclusions you could make out of these computations? So what this suggests? Yeah, yes, go ahead.
Maybe like in the earlier stages, separating the computation and like computing the response for some part of the image, then going to the further layers for that part of the image to save memory. If not all parts of the image are needed, for example, in the next layer for input for all neurons, something like that.
Yes.
Like there's a memory bottleneck in the beginning, and then it
yeah.
diminishes.
Yes, now you nailed it. So the memory bottleneck is this thing. What else? Maybe some other observations? Okay, maybe the other observation is that this first convolution is cheap because the input image has only 3 color planes, so this is like only 3 channels. Whereas in the middle of the network, you need to map like this. I don't know, 256 channels to the 512 channels, and then this is much more costly computationally. But then the computation is constant thanks to these scaling laws. It doesn't matter where you apply, in which layer you apply this, like a smaller number of channels but higher resolution, or larger number of channels or the reduced resolutions. It's kind of flat in the computation. That's good, right, for us. This maybe justifies why to use such a scaling law. And now what we can do with this bottleneck? As maybe you were saying, we want to cut on this, right? So we want to maybe do less work there, or remember less things there. And if you look at this AlexNet architecture, now you realize what they were doing. So the first layer was doing like, okay, they have convolution with straight 4. So they already, the first filter is reducing the resolution by a factor of 4 by just applying this convolution sparsely. So it's not really at every pixel, but every 4 pixels in X and Y. And then immediately they are doing max pooling with also straight 2. That means, okay, another factor of actually, I have this like expanded slide. Right after another factor of resolution reduction. So basically, they have one convolution reducing by a factor of 4, and then immediately max pooling reducing by another factor of 2. So that's to try to store the least amount of activation maps in this very first layer. So you have to like quickly reduce the resolution. So if you want to work with the high resolution images, and then they were limited in the computation capabilities, so they did this like very aggressive resolution reduction, And then why you have here these two trunks in this architecture, the reason for this is also like purely engineering. They had two GPUs on the computer, and then they wanted to work on in parallel, to train it in parallel faster, right? So there was some interaction between them, but they really the reason to have that was that to do things faster.
May I have a question to this?
Yeah.
Like for me, this was like historically always motivated by lack of memory. Like we didn't have enough memory, so we had to do this. Yeah. Um, Maybe my question is different. Yeah. Like if I wasn't limited by the memory, would it be more beneficial to have more channels at the beginning or not? Yeah. Or is the fact that we have more channels later on somehow useful for the representation or not? What do you think? Is it just like engineering thing, or is it also like beneficial in some other way?
So I have two more slides, like go into a bit later networks, and there we will see a little bit the variation, but of course there will be no clear answer to this.
Like think of it, yeah? Because it's like interesting. Like
Mm.
you have, of course, you have to make engineering decisions, but it will also influence maybe performance, maybe generalization of the network. I don't know, maybe some other stuff. Yeah. So we were
Yes.
talking about this shift invariant, and now we are like, okay, this max pooling is doing basically this shift invariance, yeah, like because it's just you are reducing, so we are like insensitive at this max pooling. So this is good, yeah, but then we suddenly started to add channels, and we don't. I mean, so far no justification for it. So maybe we could have it the same, or just because of memory, or yeah.
Maybe the resolution is smaller and we have more channels because we extract more high-level features at different times.
Yes, yes, thank you. It's conceptually, it's also, I think, was the idea that you, in the end of the day, if you want to classify your input image, you don't care about the spatial location of the things. So you just want the some representation which you could classify regardless of the positions. So you kind of want to progressively get rid of all the spatial information of the locations, and yeah, to have like a complex representation of the whole image, right? So like a higher level features. Yes, from that side it also works. So the purpose of reducing the resolution and increasing the number of channels maybe is that, but what I'm saying is that like it's also a lot governed. This architecture design was a lot governed by the engineering considerations, and of course they also have the effect on the performance.
So would you consider it like, is it like reasonable to think of it like, okay, we have this shift invariance, but sort of there's still like this first filter they see just small image patch, yeah. So there the variance is there like let's say limited, yeah. But as you see more and more, which is what this max pooling is doing, so the variance in the data increases. So it's reasonable to think that you will need like more capacity to represent this, even though you are already reducing some of it. But if you don't add this capacity, maybe you won't be able to represent the variety of your data. I think this was like reason why people started to do it, apart from this memory limitations. Yeah. Maybe Sasha will get to it, though. This is just like, I mean, when we are discussing this, like.
I had maybe still want to comment to that direction. So here we have like several layers of these convolutions, which we know they are spatially equivariant, so they gonna like preserve the shifts, and maybe we interleave them with the nonlinearity, so in the hope that we will represent not just linear but like some more complex shift equivariant processing. But then we are doing this pooling, which is shift invariant, so at least locally in this local window. So we are kind of going towards the our output for classification, which would be more robust to the local deformations of the image and to the placements of the object in the image, because we are doing that progressively. Okay, but still about this engineering thing. So it's like a lot of in these networks, like which specific network and how you design was maybe governed by also by this. And we see now it was like affecting clearly the design of this first network, maybe not so much for this later VGG network. So they could afford, okay, maybe 3 layers of these convolutions even in the full resolution, 2 or 3 layers, I don't know. And then they were reducing by half and then doing more convolutions there and so on. Yeah, by the way, like this little computational complexity here tells us that we can use just larger special filters in the first layers because that's going to be cheap. So that's cost us nothing. And in this AlexNet, they did so. They did like was that 11 by 11 special filters in the first layer. Whereas in this VGG, they said, okay, actually, if you use the small ones, 3 by 3 filters, but use more of them, this is sort of more flexible and learns better for them. But overall, this costs us significantly more memory, right? And then you can also see that somewhere, so with regard to the memory, so then the memory taken by the weights grows quadratically with the number of channels. So somewhere here, it is like 2 megabytes, 2 millions of weights per the convolution. But then you suddenly discover that in this last layers that are like fully connected, the sort of multi-layer perceptron on top of the network, you need, they use maybe 100 million weights in the fully connected layer. So it was not like very maybe efficient design from the computational and the model size perspective. But you did experiments like that, so you are like increasing the number of hidden units, and then it helps generalization. So maybe it is working the similar way here, that if you just like increase the widths more and more, that does not hurt you so much, but actually the training still works well. Yeah, what like my takeaway, my point about showing you all this network is that in whatever convolutional architecture you take, typically there would be these stages of the resolution reduction with preferably less work done in the stage 1 because you want it's memory expensive, you want to reduce the resolution. And then you could like afford to put more layers here in the deeper stages because that takes less memory, where the weights are still not as expensive and these activation maps are also cheap. So you could have like more layers at this sort of deeper stages. And this is what all these ResNets are doing as well. So then there would be some first stage of resolution reduction. So here they reconsidered it. They said, okay, no, we want to save still on the activation memory. So the first stage is going to be some chip processing to reduce the resolution by a factor of 4. And then there would be like 4 stages again. And in each stage there would be many layers now. I don't know, ResNet 50, it has whatever, maybe 8 layers in each of these stages. So some complex blocks. We'll not go into details of that, but the point is that okay, you're still doing this some equivalent processing in that part, and then you're doing some kind of pooling to reduce the resolution. Yeah, so this is kind of overview of from the design and the architecture side without going to details. So you obtain some deep network by combining this equivariant and invariant layers and taking into account also some engineering considerations, you end up with this. But the interesting things then happen. So if you train this new deep neural network on some tasks like, okay, the task is to recognize places. So I give you an image and the task is to classify whether it is a bedroom or some town square or something like that, or the city park. And it turns out that then if you want to kind of try to inspect how this network actually doing the job, what it is doing, is it computing some frequencies or textures or something else. So you could look at some specific layer, maybe at layer 4 of the network, and see where the activation to the maximum responding neurons in these layers are coming from. So you kind of backtrack it through this max pooling where it was picking from. And you see, okay, if it is the scene of a bedroom, then you see that this lamp, this has kind of special lamps which are often found next to the bed. And then so it is actually detecting them. And so on. So they found neurons that are detecting some common objects, like, okay, so these wheels in the object recognition network and this places network, they have these lamps and maybe some swimming pools and things. So it does internally, without supervision, it does learn to some neurons learn to react strongest when there are some objects. So it learns to recognize some parts, and then from these parts it makes the conclusion that, okay, this is a bedroom. So it does sort of, it coincides with the intuition and inspiration of what we wanted, that we would like this processing to be hierarchical and compositional in terms of the parts. So it does have some of that, even without you specifically engineering something, which is interesting. Right, so it's by like appropriate architectural design, we got good generalization and this sort of organization properties. All right. So now maybe this was maybe compressed about all the convolutions and convolutional neural networks and from different sides. But now I would like to come back to this principle of the invariances and the covariances and ask the following question. Okay, so can we apply this in some other context, right? So it maybe it is quite obvious that if you slide this template over the image, you get in something equivariant, but does this principle transfer to some other tasks, to some other settings where we are processing not the image but maybe something else? And how, from our wish to have equivariances with respect to something, we could how this could steer the design of our neural networks, right? So this, and I'm giving you now example of that. And it turns out that the good example is to look at the networks that are working with set of inputs. So this is, there could be different tasks where you have a set of inputs. A set means that the order is not given, so you have the elements, but you don't care about which element is first and which is the second. And this nice example to visualize is it gives you, okay, so you have a set of points. Maybe it is a 3D scan of the object, and you have a set of points. The order in which these points occur, it doesn't matter, only their position matters. And then you want to solve the task like, okay, classify this object, or maybe segment the parts, or, okay, segment the semantically. This, in the context of this task, the object can be rotated and it could maybe spoil everything for you. And we are not going to deal with that. So it's possible to deal with this rotation equivariances and invariances, but it's far more complex, and there are no like really good recipes coming out of that for the neural networks. So, and in particular in this point net network, they did not deal with that. So they would just sort of normalize the orientation, but maybe computing the PCA of these points and then um, rotating it to the frame of the PC and then doing the stuff there. So we are not concerned with this 3D orientation of these things, but we are concerned with only with this permutation invariance. So you have a set of points. Each point holds its coordinates. What do you do with that? So how do you design an architecture to classify this object or to semantically segment this set of points? One thing is that this permutation invariance, so if you swap the two of the points but keep their positions, you want to have the same results. And the other thing is that how do we actually propose an architecture which can handle the arbitrary set? You know, it could be 10 points or 500 points. So we need to tackle these questions. Now, it's actually something that we can also easily do, at least on fingers, about the permutation invariance. So suppose you have these inputs, and these are like neurons. Think of the multi-layer perceptron with one output. And you want to make a linear transformation. What linear transformation it can be such that it is invariant to the permutation of these inputs? As a linear transformation. Yeah, just the sum. So, right. So the weights could the only thing what you could do is to put equal weights on all these points, because if they are different and if you swap them, it is going to be a different result. So that's the only invariant linear transformation. And so here they've proven a more general theorem that says, okay, an arbitrary function, not necessarily a linear transform, right, but arbitrary function of an inputs, if it is invariant with respect to permutation of the inputs, it can be always written in such a form. So it must be a sum, right? But the inputs could be transformed by a nonlinear function. So maybe they could be vector inputs, and then could be vector valued nonlinear function of each input separately. Then they are combined by the sum, and then there is one more function creating the output. So this works also like for any function of n vector inputs to some vector valued output. They exist such representations. So this they proved that you could arbitrarily well approximate any permutation invariant function by this form. Maybe an example of that is maximum of x1 xn. You could approximate this by what? Okay, t logarithm sum the log sum x function, known as the smooth maximum. Right? You see, so that's you take the sum, some nonlinear transforms, and then a nonlinear transform on the output. Fits. The catch here is that this decomposition is pretty much like, so it is a universal approximation result, right? So any invariant function we can approximate by this, and then it's possible to design either these two functions, and then it will do the job. And it is in the sense similar to this universal approximation theorem that we had for a neural network with just one hidden layer, because this phi is kind of doing the job of one hidden layer, so it embeds each input into some vector space, and then you having the phi, and the row is like one more layer. But it does not necessarily will generalize well, as a neural network with one hidden layer also does not necessarily generalize well. The catch is here to approximate well an arbitrary function. The result of this phi may be very, very high dimensional. So it might not be sufficient to just map each input to the representation of the same dimension, but it might to approximate particular kinds of functions. You will have to map it to very high dimensions, then take some in that very high dimension, and then map back with the throw function. So that's not like yet very practical. And the practical way would be to construct some invariants in like a classification is actually to use more of the equivariant transforms and then to do something like equivariant, 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 equivariant. So stay in general, maybe approximating arbitrary equivariant function and then doing something invariant in the end, and that will give you the classification. Now, let's continue our exercise. What if I ask you what is the linear function? So now you have here this 1, 2, 3, 4 outputs. What is the linear function which will be equivariant with respect to permutation of the inputs? Hmm? So that matrix of ones will take the full average and put the same average in all of the outputs. Yes, that's equivariant, but it's also produce all the same outputs in all these neurons, so that's kind of not very useful yet. So it's like taking the invariant and then duplicating, right? Maybe the hint is that when you're composing the result for this output, you can possibly use this input because whatever permutation you do, you're kind of permuting the positions together, right? So in terms of the permutation equivariance, so what you want is that if you permute the input, then the output permutes in the same way. So you kind of always the same input and the same output, they stay together. So you could use your equivariant stuff like at average. Yes. Yes, could be. That's good. That's something useful. But then you are not using this input at all. You almost got it. We can then make a linear combination with arbitrary coefficients, and that stays equivariant. So you take like xi, so you take alpha xi plus beta sum over j different from I xj, and that's something equivariant. And it turns out that this is all that you get. So people proved that. So this is here in this line I'm showing this in the matrix form. So there is the identity matrix plus with some coefficient plus the this outer product of ones is like sum of all the input elements times the other coefficient. So this is if our inputs are vectors and not just the numbers. So if our inputs are vectors, that you have this matrix of weights times the vector of input set at this position.
Maybe I can get it like why you can permute your outputs together with your inputs. It's like, okay, I get some inputs and the computation is sort of fixed. What is the scenario? I don't see it, sorry.
This scenario is that you have this point cloud. At each point there is sitting some vector of features. In this basic example, these are just numbers which are in these individual circles, but they could be vectors of features. And the scenario is that, okay, you want to have a processing on this set of 4 vectors such that if you have to like supply it in some order for any computation procedure. So suppose you supply them in the order 1, 2, 3, 4, and then the result will be computing something. And then if you, for this one, if the computation is, the result of the computation is this, then if you change these numbers, so if you supply to the network this in the different order, then you want the results still be the same. So, or I could say, oh, okay, so if I place this vector not here but there, right? So if I swap these two, the result should stay the same. So the output goes together with the input.
So I mean, what was confusing for me, maybe I don't know, maybe others got it right, was that you draw it as a multi-layer perceptron.
Yeah.
Where the errors are typically fixed.
Yeah.
Now the computation is different. They're just like trying to illustrate this combination of the information into some new value.
Yeah. So this is for the case if you have not a variable set of points, but 4 points always, and then suppose you wanted to solve the task with the help of multi-layer perceptron, and then in the multi-layer perceptron the inputs are ordered like this, and then let's see what is the how we can achieve equivariance using the stupid perceptrons, and then it's this.
Can I try to check my understanding? So basically what this says is that for one of the inputs, so for example for the current input we can use any weight possible, and then all the other ones we have to like weigh as if they were in some arbitrary order, so we have to weigh all of them like the same.
Yeah. Let's look at this diagram here. So it's now not a multi-layer perceptron, but it's our set of vectors, and we put them in some arbitrary positions. So you could think of like a fully connected graph of all the inputs, and then we are doing the following computation, that we transform each of the other feature vectors by one linear transform, and our own feature vector by the linear transform A, and then combine everything together. And we are doing exactly the same procedure at every location. And that's gonna be our linear transform, which is spatially equivalent, and it is the all of the linear spatially equivalent linear transforms that you could get. And then what we can do, we are doing it in a simple way. So do that kind of equivalent linear transform, then non-linearity, and then stack many layers like this, and then you get something like this. That will be deep set architecture. And the theorem that this architecture is also a universal approximator. That any equivalent function can be approximated by this, by chaining this equivalent linear transforms with some nonlinearity, maybe ReLU in this case.
So maybe I do my understanding of it, because you said that they will permute together, but they will actually not move at all, but by just making this construction, the values will permute together, yeah? Maybe that was my confusion. I thought that you need to somehow reorganize the units, but the units do all the same computation. So, no, actually.
You know what?
Because now if the alphas are different for different neurons.
No, alpha and beta are constants. Yeah, they are the same for all of them.
I think
The same, and then the values stay. Okay.
I think the perceptron model is kind of like making this confusing. Like thinking about that set structure of neurons, this
Yeah.
This would kind of be like a for loop, basically, where you go through each input point and you compute like with matrix A, and then you sum up all the other points. And
so that is the other way, but you can implement now. Now I see you can implement it really like multi-layer perceptron. You just have to have alpha and beta the same, and then it's obvious that it will be.
Yeah, you can, yes. So you know only these two coefficients, and then whatever the number of points is coming, you can construct such a you could compute what are the weights here, and instantiate it as a multi-layer perceptron with the weights satisfying these constraints. Okay, so this is very nice deep set which we built out of the equivalence properties. And then no, okay, I'm running out of time. I wanted to connect it a little bit, so we will have a lecture on graph neural networks, and I wanted to jump ahead a little bit that now if you have not only the points but also some links between them and maybe some information on that links, you would like to make some more sophisticated processing, maybe to recognize molecules or predict chemical properties of some molecules and stuff like that. So if the molecule is represented by a graph or some properties in some social network or the computer network, then you care also about the links. So here you could think of that as a like fully connected graph without any information on the weights or just a set of vertices, but here we have also some links and somewhere no links. And then we care about being permutation invariant, that our network has to be permutation maybe equivariant to build many layers, and then do the invariance if you are doing classification. But here it's like a little bit more tricky because okay, actually, intuitively, it's not as more tricky. So you have to now design it such that the processing does something at every node, maybe looking at all the other nodes or all the neighboring nodes according to the graph, without so the processing must not depend on the actual number of this vertex or the number of the other vertices. So it can depend only on the local features at these vertices. And then you can build something like equivariant. For example, you can have a convolutional graph neural network or the graph neural network with attention that depends on also like, okay, so it compares the features at this node and at that neighboring node, and based on the how much they are similar, it does something. Or even a more general form that's message passing, that okay, so first each edge, and depending on the edge and depending on these two features, it is creating some sort of the result in message to this node, which could be even a multi-layer perceptron itself. Yes, these are all equivalent designs, but it turns out that it is not sufficient for many of important problems because there is no uniform approximation guarantee anymore. It turns out, for example, that all these networks, they cannot count the number of cycles or distinguish maybe a cycle of 4 elements from a cycle of 3 elements. So some basic things on the graphs, which we will cover that in details in the further lectures. But my kind of point of view, or why I'm bringing it here in this lecture, is that the reason for that is that yes, they achieved equivalence easily by design, just by creating an algorithm on the graph, but they did not explore all of the possible equivalent models, and this is why there is no uniform approximation guarantees, and this is why it cannot do certain jobs well. And then people came up and say, aha, let's do it systematically. Let's do from the first principles and see what is gonna, how it could work and satisfy these equivalences. Maybe May I talk for 1 more minute? This is my last slide. I just like, okay, the message. Now the crazy things start to be happening. So they say, okay, we're gonna put in each node a positional encoding. So we will somehow we want to know where, like globally in this graph, this node is occurring, but this positional encoding has depend only on the graph, but does not, it has to be also like permute with the node if we represent the graph in the different order. And it turns out that a good positional encoding appears to be the eigenvectors, so the Fourier basis for the graph. There is a Fourier transform on the graph. There is a generalization. So if you have a chain like this is also a graph, right? You could think of this shift operator on this chain, and there is this corresponding eigenvectors of the shift operator, and this is the Fourier basis for the chain. If it is a more sophisticated graph, there is still eigenvectors for that graph, and corresponding there is a corresponding basis, and it's possible to say, okay, so there is a Fourier transform on the graph, and for some reason it's good to have positional encodings. So by the way, so for the chain it would be such positional encoding, right? As this from the full common Fourier basis. But it turns out that for graphs it's also a good thing to have it there, but the problem is that to compute this Fourier basis for the graph, you gotta do the eigen decomposition of graph Laplacian, and this is then gives you the basis up to the flips of these eigenvectors. And then they say, but now we want to be invariant with respect to the flips, or even better, to be equivalent with respect to the flips. And then you could really, by doing this, you could certain tasks like the counting substructures in these chemical molecules, or I don't know what, it then start performing. It matters in practice as well, like doing this till the end, these equivariances. Okay, so that was like looking ahead and overview into the graph neural networks, and like justifying for these ideas of the invariances and the equivariances. Thank you. Sorry for the overtime.